Hello, good afternoon, everybody. We are now starting the webinar, and okay, welcome everybody. And this is the third webinar organized in the framework of ECCSELERATE project. And the webinar is organized by Sotacarbo and OGS with the participation of the BGS and IFE. So before starting, I would like to give you some recommendations. So we kindly ask you to all the participants to switch off the microphone and camera during the webinar. And we will have at the end of the two presentations a question session. And we ask you to type your question in the panel, in the dedicated panel. You will have probably on the right side of your screen, and we kindly ask you to specify the name of the speaker you would like to address the question. So let me give you a brief presentation of ECCSEL ERIC. What ECCSEL ERIC is? ECCSEL ERIC is a European research infrastructure on a carbon dioxide capture and storage laboratory. The consortium is composed by 5 countries: Norway, where the operation center is located, France, Italy, United Kingdom, and the Netherlands. The infrastructure provides more than 79 world-class research facilities to both research and industrial communities. And the facilities are owned by 21 facility owners. The aim of the project is mainly to close CCUS knowledge gaps, contribute to reduce CO₂ emission in accordance of Paris Agreement, and overall to reduce the effect of global warming. ECCSELERATE project is a 3-year project organized and managed by ECCSEL ERIC, and the budget dedicated is 3.5 million euros. The focus of the project is to increase the use and long-term sustainable operation of ECCSEL ERIC infrastructure, develop, assess, and services dedicated for industry and SME, and increase internal collaborations. Within the ECCSELERATE project, a specific capacity building program has been developed, and it consists of 3 main core activities. And they are a webinar series, and today we are attending one of these, a specific workshop, and tailored training courses addressed to attract industry and researchers or other new groups to ECCSEL ERIC. So here is the webinar series. The webinars are dedicated to 4 main topics, as you can see, and they are capture, transport, utilization, and storage. The webinar series started last year in October, and we presented 2 webinars, and now the webinar is on today's webinar is on storage, and specifically a characterization of a CO₂ geological storage site. And if you would like to see the program, you can go to the website. Today's agenda. Today we have two nice keynote speakers, and we would like to thank them. And they are Karen Kirk from BGS and Stéphane Polteau from IFE. And I am Valentina Volpi from OGS, and I'm giving this brief introduction, and Federica Donda, my colleague also from OGS, will manage the question section. Okay, so please, Karen, go ahead with your presentation. And let me give you a brief introduction of Karen as soon as she will. Okay, so the presentation of Karen, as you can see, is on risk assessment-led site characterization. And Karen is a geologist at the British Geological Survey working in the Decarbonisation and Resource Management Challenge. She has worked on projects focused on the geological storage of CO₂ since 2001. Her experience is mainly in assessing sites for storage capacity and suitability to store CO₂, as well as risk assessment as part of site characterization. So please, Karen, the floor is yours.
Oh, apologies, I couldn't seem to unmute myself. Hello, thank you, Valentina, for that introduction. I hope you can hear me clearly. Thank you for inviting me to talk today. So I'm going to talk to you then about risk assessment-led site characterization. So what is the role of risk assessment in site characterization? Well, site characterization is about understanding the risks to secure containment of CO₂ at a specific site. Characterization led by risk assessment helps us to anticipate risks, and then hopefully we can reduce those risks or mitigate those risks. Or if we can't do that, then it will help us to monitor those unmitigated risks. It can also determine what site characterization activities are required. And it also ensures that resources, time and effort are focused to meet the objective. So first of all, we need to carry out an initial risk assessment. So this is an example of a risk assessment exercise that was carried out by an EU-funded project called the SiteCar project, where they were looking at a specific site. They initially identified 79 risks that needed to be addressed. And each of those risks were described and categorized. So they were put into 12 categories that are listed in the table you can see there in the right-hand column. Those categories were then placed into 5 overarching risks, those that you can see. So containment risks, adverse effect on other resources, reduced technical performance, monitoring and regulatory, and economic and environmental. So the highest risks that were addressed and highlighted by the SiteCar researchers were containment risks and adverse effects on other resources. So once we've identified our risks, what do we do with them? So we give them a score for probability, which is the likelihood of a risk occurring, and also for severity, and that is how bad the impacts are if that risk were to actually occur. So once you've scored them, you can plot your risk onto apologies, it's not working. You can plot your risk onto a risk matrix that you can see illustrated on the left of the slide. So we have a risk there that's plotted in the very high to high category. And once you've highlighted where that risk falls, you can then take it forwards and try and undertake some mitigation actions to via site characterization and looking at geological risk to try and reduce those risks. So we carry out things like modelling, etc., to try and reduce those risks so we can bring them down into that lower area. So we put them into a medium to low risk area on our severity and probability scoring. So what can we do in terms of activities to reduce these risks then? So we can carry out dynamic modelling and we can carry out regional flow path migration analysis, and this will help us to predict the direction that the CO₂ will travel in. We can carry out numerical simulations to look at the integrity of abandoned wells, because these could be potentially provide a leakage point. We can also carry out geomechanical modelling of the CO₂, so we can assess the effects of changes of stress as we're injecting. We can carry out an assessment of the shear failure and potentially predict whether we may cause any fracturing. An evaluation looking at the effect of geochemical changes associated with CO₂ injection is also useful in terms of looking at whether we have any reactions within the pore fluid whilst we're injecting. And also we can carry out an appraisal of geological hazards, such as potential leakage points in the shallow subsurface. So once we know what the risk is, we can then go on to try and build a model of our geological storage site. So we build a static model. This is basically to try and represent the geological features within the storage site that we're trying to investigate. So we start off by creating surfaces of the reservoir rock, of the cap rock, and we do this by using interpreted seismic data, or we can use published map data, or a combination of both. And we also would like to include information about faults and things like wells into the model. So once we have our surfaces, we're happy with our surfaces that we've created, we can convert these surfaces into a model which contains cells. We can then assign properties to those cells, for example, the porosity and the permeability and the facies of our site. So the figure on the left shows a simple geological model with a reservoir layer overlain by a cap rock, which have been assigned cells. A model needs to have the cells applied so that we can assign the geological properties to it. But the grid cell size is really important for the simulation stage of the model. If your grid cells are too large, it can produce an inaccurate representation of the geology and also of the predictions of the CO₂ being injected. If your grid cells are too small, this can increase the amount of time to run the model. So we really need to get the optimum amount of grid cells to make basically a representative model that will actually run efficiently as we're running our simulations. And as scientists, we do like to try and reflect the small scale geological changes as much as we can, but this just requires too much computer power. So the challenge basically is to try and keep the most important geological features represented. So we also need to include faults in the model. So we do this by plotting the center lines of the fault polygons to model the locations. And it's usual to orient the grid of your cells that you've produced to follow the dominant trend of the faults. This allows us to create more uniform cell sizes and shapes, because if we get non-uniform shapes, it can cause inaccuracies around the fault areas and cause problems when it comes to carrying out our simulations. and smaller faults may be omitted from a fault model as it may not be deemed a risk. But as you can see, so we've modelled in this model the faults that we deem to be the biggest risks, and it follows through our layers to the top of the overburden of the model. So once we're happy with the model that we've created, we can then start to assign our geological properties to that model. So we include information like the depositional environment. This is represented by the FASHES model. So that can be, it's been deposited in a river, or it's been airborne, or it's been an evaporite within a lake type situation. And the FASHES model represents the variation in porosity and permeability of the strata due to the different grain sizes and the material of the host rock. The porosity will help to estimate the amount of storage capacity available in our target site. And the permeability will help to estimate the flow path of the CO₂ as it's injected. So once we're happy with all that, we then can move on to building our dynamic model. So a dynamic model can be used to model in the well or near the well. It can also be used to model within the storage site, within the storage complex, which encompasses the cap rock and the rocks that underlie the actual reservoir. And also it can be used to model at regional scale. So we take our model with cells from the static model, we decide on the boundaries for the model, and also we can then go on to carry out our flow simulation. So for that we will require some additional information, for example, pressure, temperature, geochemical information, for example, salinity of pore water. We need information about the phase that the CO₂ will be in when it's injected, and information about the rock properties. So I'm just going to show you a case study. So this is an example of a risk that you might have chosen from your risk matrix. So we're looking at a site that may encounter pressure buildup during injection. So this is based around an area in the southern North Sea. It's the Bunter sandstone formation that we're focusing on. And the risks related to pressure buildup during injection. So the dynamic model for this was built from a depth map and a thickness map. And then we got porosity and permeability data from core plug data. No heterogeneity was included into this model because it would have made the number of grid cells in the model impractically high to be able to run the model. On the map there, we have plotted some observation points that we will observe during the simulation of this site. So they're numbered 1 to 5. And the observation point 1 is actually also an injection point. The depth to the reservoir varies from about 0 to 2,800 meters, and it's partially bounded by faults and salt walls. So these are the parameters that we've included in our model. So the picture shows the top surface of the Bunter sandstone. It's strongly affected by salt movement in the underlying zechstein group, which is a salt. It typically lies at depths of about 2,000 kilometers, which is the light blue areas on the map, but it also reaches much shallower depths, which sits situated above those salt domes where it's been pushed up from beneath. And they're the sort of orange areas on the map. And these will be our target for where we start to try and inject CO₂. So we assume the lateral and underlying boundaries are sealing because we've got those faults around the edges and the salt walls. And we've actually raised the permeability slightly of the cap rock because we do have faults that actually extend from the reservoir into the overburden, into that cap rock. So we need to allow for that. So this is where we started with. Our initial strategy was to use one injection point where we were injecting 10 million tonnes of CO₂ per year. And this was for a period of 50 years. So our aim was to make sure that we could limit the pore fluid pressure rise to approximately 75% of the lithostatic pressure at the injection point. So the image on the left here shows the pressure increase in the sandstone at 50 years. So injection has just ceased. The pressure increase around the edges is quite negligible, really. There is a slight pressure increase in the blue colour, but around the injection point, the increase is quite significant. And the graph on the right shows for around the injection point, which is the OP-IP1, it's labelled in a blue colour. It's actually the pressure right at the start of injection increases right up to just below 12 megapascals. That does reduce over the injection period, and we get to 50 years and it's down to about 7 megapascals. But this is significantly high, and we really don't want to risk this kind of scenario. And you can see the pressure is also increased in the other 4 observation points. And after injection ceases, the pressure does actually recover quite well. It does fall quite fast, rapidly. And we've projected the graph to show up to about 1,000 years after the initial injection started. And it does recover well, though it doesn't go back to what it was initially. So what do we do? How can we try and combat this issue? So the next thing we tried then was to increase the amount of injection wells we had. So we've got 12 injection wells. That includes the original injection point that we had in the first scenario. So injecting 1 million tonnes of CO2 per year per well. So we're balancing it out across the formation, which seems a sensible thing to do. So you can see the difference there in the pressure increase across the map, the pressure footprint. There is an increase again around those injection points, but it's substantially lower. In the observation points 2 to 4, it's probably at least twice as low as it was in the previous scenario. And obviously in the injection point 1, observation point 1, it's significantly lower. It's down to just over 2 megapascals there. So that's fantastic. We've managed to resolve the issue of the pressure increases, and actually it's increased the storage capacity too. We've managed to store 60 million tonnes over that 50-year period. So once you've gone through, you've modelled your risk, what do we do next? So we look at the risks again in terms of where we started. We'll go back to our risk matrix. This is the process that we followed. We started off with, on the left there, our risk was up in that very high area. We took it through to the modelling stage. We modelled it. Obviously we weren't happy with our initial scenario, but we managed to resolve that. We've brought those probability and severity scores right down so that we can move that risk down into a medium to lower level area. And that's fantastic. That may not always be the case though. You may come across a risk that it doesn't particularly, you can't manage to resolve it, or it may well bring up something else that you need to further investigate. So it may highlight you've got further modelling work or further laboratory work to carry out to try and resolve that issue. So this is an iterative process here. And this can be repeated. And obviously, if new data becomes available, then it is recommended to repeat the process. So just to conclude then, risk assessment-led approach, it basically ensures resources, time and effort are focused. We can reduce risk ratings by mitigation actions. So for example, using dynamic modelling, CO2 flow predictions, fault and well integrity modelling, plus many more. A geological model will never be identical to the real world, but it's only as good as the data you have. So model performance depends on the quantity and quality of data. The model will reflect the reservoir behaviour if the reservoir is accurately represented. And models may evolve over time. So, I mean, that can be dependent again on newly acquired data. So just to highlight some of the facilities that BGS have got in terms of the ECCSEL facilities that are related to site characterisation. So we have the Transport Properties Research Laboratory that can carry out several different types of experiments. So we can look at intact cap rocks. We can run many long-term experiments. We've had experiments running for years. It can look at physical processes to inform models. It can carry out multi-phase flow through low permeability materials and look into capillary entry pressures. It can also carry out experiments in terms of faults and fractures as well. So we can look at flow through faults. We can look at monitoring of shear and normal stresses. Also have a look at implications for long-term fault sealing behaviour, and also wellbore and cement integrity. And then we also have the Rock Mechanics Physics Laboratory, which can carry out bespoke experiments. These experiments can be applied to fractures, faults and earthquakes, and can be carried out at a macro or micro scale. And that's it. Thank you very much. Thanks for listening.
Okay, thank you, Karen. You will be contacted at the end after Stéphane's presentation. So Stéphane, I now assign you the screen, and so I will introduce you. Okay, Stéphane, can you open your presentation?
I thought I did. Share. Yes. Okay. And now you see it?
Okay, perfect. So let me introduce you, Stéphane. Stéphane Polteau is a senior research scientist in the Reservoir department at IFE, where he has been working on the interpretation of strontium isotope data in terms of reservoir characterization. He's also involved in a wide range of research topics, mostly related to fluid migration in sedimentary basins, with a special interest in developing tools to detect natural seepage of hydrocarbon for exploration. So please, Stéphane, go ahead.
Thank you very much for the introduction, and I just see myself, okay, and organizing the webinar. Okay, so I will talk about the characterization of fluid connectivity of carbon storage sites using strontium isotopes. So this is method presentation because I'd like you to understand how this geochemical tool works, and maybe you can apply it to your own workflows. And because we're not all geochemists, I'll start with the basics. So isotopes are variations of a particular element, for example here carbon, and they differ by the number of neutrons, so they have different mass. So for example, the 8% mass difference between carbon 12 and carbon 13 indicates that some of the processes will favor one of the isotope over the other. So this process is called mass fractionation, where the ratio of the heavy over the light isotopes have values that reveal physical, biological, or chemical processes. For example, photosynthesis, respiration, evaporation, or I've been using to differentiate the origin of methane between biogenic or shallow origin to thermogenic, deep origin. We also have radioactive isotopes. So these are unstable and decay with time, and they are used to date minerals and other substances, but we're not going to talk about them more. But then the talk is about strontium, and strontium is different from carbon because it is heavier. It has an atomic mass of 38. That means that the isotopes 87 and 86, the mass difference is too little to cause mass fractionation, which means that the isotope ratio of 87/86 doesn't fractionate and can be used as tracer. So there's other application like in forensics where you can make sure that what is in your bottle of wine or champagne or whiskey corresponds to what is written on the label. But it's been used as to study migration of population by measuring the strontium isotopic ratio of tooth of animals that can correlate to specific geological provinces. Because the rationale behind this is that the isotopic ratio of the rock is not going to fractionate, so it will be preserved from the rock into the soil, into the plant, and finally assimilated by the animals that consume those plants. So you can see this is just a quick glimpse into the world of isotopes and your creativity. You can do many things. So the strontium is the 15th most abundant trace element on the Earth's crust and is found mostly in seawater. And it's also in carbonates because it substitutes for calcium. And we also find it in other silicate minerals and clays because it substitutes for potassium. There's two main sources of strontium. There is a continental source and a mantle source. So the continental source consists of various igneous and granitoid rocks and the exhumed carbonate platforms that would release the strontium by weathering, and the strontium will be transported by rivers into the ocean. The mantle source would supply the strontium directly to the ocean at the mid-ocean ridge by the hydrothermal alteration of seafloor basalts. So all the strontium in solution in the ocean can precipitate as carbonate or be included into sediments like clays, and in turn will be recycled by metamorphism or subduction. So strontium is where the ocean is where we find most of the strontium, and because the ocean is very well mixed, Weiser could draw this evolution of the isotopic composition in strontium of the seawater through time, which means that so it's well mixed, at any given time, the isotopic composition of the seawater is constant. And you can see that this curve oscillates between the values of a continental source and the mantle source. So this curve has been interpreted as representing global tectonic cycle. So where the curve goes towards continental source values, it's interpreted to represent increased weathering caused by mountain building. When the curve goes towards the lower value, towards the mantle source, it's interpreted to represent increased mid-ocean activity and ocean spreading. But the point of this slide really is that to say that at any given time, the composition in strontium isotopes of the ocean is constant. And this is important because when you start to accumulate sediments on the seafloor, you will trap in the pore of those sediments some of the seawater that has this typical composition at the time of deposition. Of course, the composition of the water will start to evolve and change during diagenesis, during mineral precipitation and dissolution. And these changes will be controlled by the lithologies, the type of sediments that are being accumulated. So as burial continues, the trend would be that the formation water composition will try to homogenize. The differences will remain where different water bodies will be separated by low permeability barriers. And this is the whole logic behind using strontium isotopes to characterize the fluid connectivity in sedimentary basin and within sedimentary units and then in reservoirs. So we can measure the strontium isotopic ratio in the formation water when the water samples are collected during drilling. But the problem is water samples are not collected so often. So the way around it is to measure the strontium isotopic ratio from the salts, the residual salts from the formation water. and this is the method called strontium residual salt analysis that was developed by Craig Smiley at IFE in the mid-80s. So the residual salts are the salts that are left behind from the formation water after the formation water evaporated. So all the salts are left in the pore network of the rock. So what we do is we take our core sample, we gently crush it by hand, and then we soak it in pure water to redissolve the salts. So this solution after is filtered, and the strontium is extracted, and the strontium isotopic ratio is measured into our fantastic instrument here called the Neptune Plus Multi-Collector ICP-MS, which is part of the ECCSEL infrastructure. And so this instrument is used for reservoir characterization using the strontium isotope. That's what we use it for. So when you have analyzed your core samples, you can plot them versus depth, and this is a good example of strontium profile going through oil reservoir. So in the case of oil reservoir, the strontium profile represents the condition at the time of oil emplacement, because the oil that remains is trapped as isolated droplets in the oil phase. So with one well, like in this case, we can assess the vertical reservoir connectivity. So for constant homogeneous composition, we interpret as indicating connectivity. We interpret mixing trends, like here, as representing limited connectivity because the homogenization is not complete. And we interpret breaks in trends, indicating the location of low permeability barriers separating isolated compartments. So in the end is the smoothness of the trends and the scale of the breaks is reflecting the degree of homogenization, which is controlled by diffusion. And because diffusion is a slow process, then the strontium data is really amplifying heterogeneities in the reservoir that cannot be detected when using other methods, other measurements like pressure that would equilibrate faster than diffusion. So when we use 2 wells, we can start to evaluate the lateral and the vertical connectivity, but also say something about the filling history. So for example, here on the top diagram, we have 2 wells and the corresponding strontium profiles overlap. So when we have, in the lower example here, we have a compartmentalized reservoir that was filled with 3 distinct flows of oil. And if you look at the strontium trends, each flow have their own trend. So now I will finish by giving an example. It's on the Longyearbyen CO₂ lab. So Longyearbyen is the world's northernmost settlement. It's on Svalbard here. And so Longyearbyen is located here. It's extremely isolated, as you can see. Almost the closest place to Longyearbyen is the North Pole. So it has to depend on a closed energy system that is powered by coal. So you have a series of coal mine and you have your coal plant. So everything is, it's a closed system. And so it's an ideal place to demonstrate the full CCS value chain. So we have 8 wells. We have 2 wells next to the airport, which is actually next to also where the this seed vault is, and 6 wells here next to the injection site. The target reservoir is about 700 meters deep and crops out 14 to 20 kilometers northeast of Longyearbyen. The aim of the study was to evaluate the fluid connectivity within and above the reservoir units, and we had 105 samples from the 5 wells, so 1 next to the airport and the seed vault, and 4 at the injection site. And the results were published in 2017 paper by Kirk et al. In the International Journal of Greenhouse Gas Control. So for the stratigraphic sequence, we have about 300 meters thick reservoir that is Triassic in age, and then it's overlain by almost 500 meters of shale as a caprock, and there is a detachment more or less in the center. And we have about 30 meters of shallow aquifer that is overlain by about 150 meters of permafrost. When you look at the reservoir unit, that is, it's a zoom picture here, you see we have 2 pressure data. And if you put the typical trends of pressure varying with depth, you can see that those 2 trends don't align. So there is a pressure barrier somewhere in between. So when we plot our strontium data, you can see here, you can see 3 trends, more or less. 1 at the bottom, 1 at the top of the reservoir, and 1 in the caprock. So now you've seen how we interpret the data. We look at discontinuity and the breaks in trends, and you can put immediately a barrier here that fits well with the pressure. And then we can put also 1 here on top of the reservoir with the different trends. We also see a minor variability within the units, but they do not seem to influence the main trend of the strontium. So these are interpreted as baffles. So we have our reservoir consists of 2 connected units, at least here. Here we don't really know, we need more points that are well connected and overlain by a caprock that appears to be sealing. So we had more samples that going through all the overburden. So we have our reservoir trends with our barriers, and we can see here we have a trend in the caprock that is quite smooth and going towards heavier values upward. This trend can be interpreted to represent diffusion equilibration, but the only problem is that the time scale for equilibrating this thickness of sediment is not realistic by diffusion alone. So another process has to be involved here. For this other trend going through the shallow aquifer, we have a mixing trend, and going to a homogeneous trend in the permafrost. So that was it. So this is my conclusion. The strontium method is very powerful to characterize the reservoir and the fluid connectivity of reservoirs. It's very useful to use even from the first well you drill. It works on old cores because you can extract the residual salts whenever your cores are dry, or you can also measure the strontium ratio from water samples. It's complementary to pressure data to pinpoint the location of barriers, because pressure data are not continuous measurements, so you usually have a scatter, and where you have a break in pressure trend, you usually don't know exactly where the pressure barrier is located. But the strontium method can also be used to characterize geothermal reservoirs, to characterize top seals and overburden, But for basin scale fluid connectivity, we need to be integrating with other geological data, like we see in the Caprock example of the Longyearbyen CO₂ lab. And we would like to combine the strontium with chlorine isotopes to be able to evaluate different scales in fluid dynamics in sedimentary basins. Thank you.
Okay, thank you, Stéphane.
Should I close my camera and mic? Yeah.
I will do it for you, don't worry. Okay. So I think that we can proceed with the question section. Please, Federica, go ahead.
Okay. Just before to move to the question session, I would like to underline that the characterization of a storage site for any fluid storage is a very complex process, and it requires a lot of analysis, different kind of analysis, and risk assessment and a proper geochemistry assessment play a crucial role. So many thanks again to our speakers for their valuable contribution. And I will now will proceed with the questions. The first one is a very technical one, which is addressed to our organizers. The question is, will the presenters provide the slides of the seminar? Yes, the slides will be available on the YouTube channel of ECCSEL. The second question is addressed to Karen. The question is, I would also be curious whether the research Karen presented can also benefit from specific research infrastructures in other ECCSEL countries. Please, Karen.
Thank you. Yes, so definitely. And just looking at the facilities that are available across the ECCSEL network, I mean, for example, the geochemistry side of things would probably be beneficial, so from Stéphane's institute. Also, I see there's also facilities at SINTEF, the fluid laboratory that looks at obviously pore volume, pressures and temperatures. There's also a geochemistry laboratory, IFPEN as well. So yeah, definitely would benefit from any research from those different institutes and ECCSEL infrastructures. Definitely. I hope that answers your question.
Thanks, Karen. The second question is also to you, Karen. The question is, which of these CO₂ storage method would yield an optimal storage of CO₂, CO₂ solubility, or CO₂ mineralization storage?
Okay, so I guess so these different methods of storage, they occur over very different timescales. So solubility would be your first stage. So personally, I would say that solubility is probably the optimal storage methodology. Mineralization storage is also important because that actually locks away permanently, will lock away our CO₂, because mineralization is where the CO₂ will react with the minerals within your reservoir rock, and it will precipitate it to form a new mineral, and it will be locked away permanently. However, this does have implications, of course, within your reservoir, because that can actually start to reduce the properties within your reservoir. You can start to clog up the pore throats, the spaces between your pore pore space between the that lies within the host rock. So while it's important, we don't want it to occur too quickly, because obviously it could affect how we can manage to carry on injecting CO2 to that reservoir. But I guess I would say probably in the long term, mineralization is probably what we're aiming for, but that would be post-injection, when we know that we're not going to be injecting into that site anymore.
Okay, thank you. We have another question to you, Karen. The question is, how is defined the maximum acceptable pressure in the reservoir, plus 75% of lithostatic pressure in the presentation?
I have to be honest, I wasn't the actual modeler doing this work, so I'm not 100% sure how they defined that. That is something I can try and find out for you, if and try and let you know it, but it'd be at a later date, I'm afraid.
There is a question to Stéphane. The same person who asked a similar question to Karen before. Could your research benefit from other infrastructures in ECCSEL? Your microphone is off, Stéphane.
Yeah, it's good, good. Yes, I couldn't unmute. Yes, obviously. I mean, there's always one method alone is as good as. I mean, you can improve the capabilities of one method if you can integrate it with other results. So yes. Okay,
thanks. There is a comment to you, Stéphane. Wonderfully presented. The reservoir rocks outcrop to the north on the injection site. What are the odds that the CO2 injected in Longyearbyen will migrate northwards and emit to the atmosphere at a later stage? I asked, can strontium isotopes tell anything about the lateral fluid connectivity within a reservoir? Maybe not. Thanks so much again.
Yes, so let's start by one of the point of the question is about the lateral connectivity. So we measured the strontium isotopes in the wells that are next to the injection site, and from one well that is next to the airport, right? So they are 7.5 kilometers away, and the results show that the reservoir unit is connected, but it's the other way to the outcrop, right? And the outcrops are 14 to 20 kilometers to the northeast. And that we should be able to tell if they're connected. The area where the outcrop is known for, there's some methane seepage there. So it's possible that the CO2 can migrate, yes. And then can I see? I think that answered everything.
Okay, thanks, Stéphane. We have another question to Karen. Could you please indicate if this is part of ongoing project of CO2 storage? Have you made the positional interpretation or just used a previously conducted study output?
Okay, so if you mean, is this an ongoing project that's actually injecting CO2, then no. In the UK, unfortunately, we don't have any live and active CO2 storage projects at this moment. The depositional interpretations are used. It is basically from data that we have. As a geological survey, we have a lot of this kind of information in our own archives, but also there's a lot of published data as well available. So it's from a combination of our own data and published work. So hopefully I've answered everything there.
Thanks, Karen. We have another question to you. If you have conflicting risks, for example, you increase number of wells to reduce the pressure, how is it managed in their overall scheme? How do you weight different risks?
Okay, so well, obviously wells, I see what you're saying, so wells do pose a threat in terms of being a leakage pathway, but obviously one of the ways you can mitigate the effects of having those additional wells is to make sure that you use well casings and up-to-date cements that we know can cope with the interaction with CO2. Make sure that it's all properly completed around the areas where obviously we know that we may have any issues with any leakage. So that would be how you'd counteract that in terms of the weighting the risks. Yeah, so I guess that's how you would take it. You would weigh it up.
Okay, thanks. You can rest a little bit, Karen, because we have now a question to Stéphane. Is it possible to use a less precise, sophisticated ESP-MS to perform strontium isotope analysis in the place of Neptune Plus? Is it possible to get information on connectivity reservoirs using a traditional ISP-MS? Maybe the data resolution will be not sufficient.
So to answer, this is a technical question. I can tell you the Neptune Plus is quite a recent instrument, and the Strontium method has been developed since the mid-80s. So they've been using different instruments. And for example, there's one study that we did at IFE. They were using a thermal ionization mass spectrometer, Finnegan MAT 262. I'm reading here. Oops. And I'm trying to go back to the question.
Okay.
And but you still need to have a very good precision, because the variation in the ratio is very minute, and precision usually you need to have down to 4 to 5 digits. Yes, the end.
And there is another question to you, Stéphane. Can the Strontium method help to determine interconnection of compartments if the age of hydrocarbons is approximately similar?
Yes, because we're looking at you see, with the Strontium you look at the water system. So it's so you get you could get a different story from what the oil is telling you. So again, when the oil is placed into a reservoir, it will displace some of the water down, and some of the water will get trapped and remain in the oil phase. I don't know if I answered correctly.
Yes, thanks. We do have another question to Karen, but maybe also to Stéphane, because it's a general question concerning ECCSEL. The question is, does ECCSEL consider research for CO₂ storage in depleted gas condensate reservoirs?
Obviously, I don't have the involvement that you guys have with ECCSEL, but certainly the research that I do and the research that I've been involved in definitely consider CO₂ storage in depleted gas and condensate fields. Yeah. And actually, the risk assessment site characterisation works for either aquifer or hydrocarbon fields. It's not specific.
Okay. Let me check if we have other questions. It seems that no. So we are at 3 o'clock. So many thanks again to Stéphane and Kirk and